Okay, students. So what we do today is we complete the rest of the topic where we look at bandwidth part to start with. And then we look at the time domain structure of 5G. Then we look at three duplexing schemes and how they differ from each other. Then we look at how, especially in TTD, things become more complex and also interesting in able to support various kind of scheduling decisions in both the downlink and uplink. This is the outline. Okay, so I think you might have seen even in the assignment where we are asking to use one bandwidth part, but in general, yes, one can configure multiple bandwidth part and whatnot. So things are more complex here compared to LTE. And if you look at in 4G, if you have, let's say, channel bandwidth of 20 megahertz, you expect all the receivers, I mean all the users in the network, to be able to listen to the entire channel of 20 megahertz. But especially in 5G, what has been done is, since the bandwidth is increasing quite a lot as you go to millimeter wave, and if there are certain users who may not really require those kind of bandwidth, for example, the applications like IoT and some of the URLLC applications, so why to ask these receivers to listening to the entire channel? Can we do something better than that? That's where the bandwidth part comes into picture, where you figure it out what part of the entire channel bandwidth a given user should be able to listen to for able to send their traffic or for receiving the traffic from the base station. It has multiple advantages. One of the main advantages that you can see here is saving the power consumed at the handset side, at the user side. Again, this is important for IoT devices, where the amount of energy that is consumed at the user side is a function of RF processing that you do, which is also involved at the baseband layer level. So by reducing the channel bandwidth, we can be able to reduce the baseband processing and RF processing. That is one benefit that you can get straight away. And other thing is, by not requiring to design your radios listening to the entire channel bandwidth, which could be like a 200 megahertz, even 400 megahertz as you go to numerology 2 and 3, you can able to design a low cost and less complex devices. Otherwise, even these IoT devices which you want to sell for low cost have to end up having a very complex radio who should be able to listen to the entire channel bandwidth. That may not be really the case to be able to really push out millions and billions of IoT devices. The idea is, can we do something smart where let the base stations are using whatever the channel bandwidth that is configured at the base station side, but from the user side, we can decide which user should be listening onto the wide channel, which user should be listening onto the narrow channel, depending on their capabilities, depending on their current traffic conditions, and depending on other logic that operator wanted to apply in deciding which user should be supported as part of which bandwidth part. Some of them could be related to the application side, like URLLC kind of thing. Where if you look at the definition of the bandwidth part, it contains contiguous range of resource blocks for any given subcarrier spacing. If we take any numerology, you can define certain contiguous, let's say if we take 10 such resource blocks together, I can call it as one bandwidth part, where you can have separate bandwidth part defined for downlink and uplink. And if you look at in terms of the user equipment side, we can have, like this is quite important, make a note of it. User can be configured to use 4 different bandwidth parts. This is in the case of release 15. And at any given time, out of the 4 configured one, base station can inform using the PDCCH. Inside that we have downlink control information. Using this, the base station can inform to the user what should be the bandwidth part the user should be using for the upcoming slot intervals. Okay. And also it is possible to have different bandwidth part configured by the base station to use different numerologies to support like URLC, IoT, and enhanced mobile broadband. That way, the bandwidth part has multiple benefits, not just about reducing the cost and reducing the power. It is also able to support heterogeneous applications, which 5G expected to cover. Let's look at the various use cases of bandwidth part. The first one that you see on the left-hand side, which is a kind of talking about supporting the users with narrow bandwidth capability. If the users are not having capability to operate on wider bandwidth, you also configure the base station to use only a part of the bandwidth. Otherwise, there are no user to serve. It is not what you really want to do all the time, but this is one extreme use case where you are also asking the base station to reduce the amount of the channel bandwidth to the subset of the bandwidth that user equipment can operate on. That is the case one. The case two is what I was mentioning in the previous discussion, where I can create multiple bandwidth part. In this illustration, you can see I have two bandwidth part. So here on the x-axis, you see here, this is the frequency domain. Okay. So what I'm talking about is we are doing the frequency division multiplexing basically. We are doing FDM where the amount of the channel bandwidth that you have is divided into two parts. On each of the part, you are configuring one of the numerologies. It could be numerology 0, this could be, let's say, numerology 1. It could be whatever it is. That way you can support different numerologies, or you can even support the same numerology. It's not need not be different numerology. Both of them could be numerology 0 as well. So that is also possible. Nothing prevents to use same numerologies or different numerologies on different bandwidth part that are part of given carrier bandwidth. The third use case is even more interesting, where you look at very carefully. We have nested bandwidth part inside bandwidth part, where BWP2 is actually a subset of BWP1. This is important for saving the UV's energy consumption while user is already connected with base station. For example, the case could be something like this. User is initially connected, let's say this is 20 megahertz. And let's assume this is 5 megahertz. So initially the user might have been configured by the base station to operate on the channel with 20 megahertz, which will give you, as you see, depending on the numerology. If it is numerology 0, so we have seen in the previous class, we have 106 resource blocks. That way we have 106 resource blocks in the frequency domain. The user can listen to these resource blocks depending on how many in the base station allocated to the user. User can start receiving it and also can transmit using some of them in downlink and uplink. What this example is showing is, after a while, let's assume that there is hardly any traffic that is coming to the user, and the network is a kind of very, very off-peak hours kind of situations. So why to ask user to transmit, basically listen to the entire channel bandwidth? You can ask the user to listen to only 5 megahertz. At a later time, if the traffic is increasing at the user side by looking at the buffer status report and other thing, if needed, you can ask the user to come back to operate at initial bandwidth part, that is with 20 megahertz. That way, you can dynamically ask the user to use one of the bandwidth part with the idea of reducing the amount of energy consumed because of not having enough traffic at the user side. That is the third use case. The fourth use case that you see is about supporting non-contiguous spectrum, where if the operator, for whatever reason, couldn't able to get the channel bandwidth of 20 megahertz contiguously, if you get 10 here and 10 here, so this is the frequency domain again. So then it takes these two bandwidth parts together to get a cell of 20 megahertz, but these are actually not contiguous. For that reason, he has to create two bandwidth parts. That is the thing. And the last one is about supporting future technologies, where we can create a separate bandwidth part and start deploying the new technologies while you have the legacy, like in this case 5G, operating on the initial bandwidth part. That is one. So all these use cases are possible by using bandwidth parts, where we are kind of having a subset of resource blocks rather than the entire set of resource blocks that are there in the channel. Again, make a note that a user can use only one bandwidth part at a time. That means, for example, in a given slot of 14 symbols, and if you assume it is numerology 0, we are talking about 1 millisecond. So in a given slot of 14 symbols or 1 millisecond, the base station can use only one of the, sorry, the user equipment can use only one of the bandwidth parts. So that way it is a kind of also disadvantage if you take this kind of approach where we have non-contiguous thing. In this case, if the user require a lot of bandwidth, but since there are two different bandwidth parts which are not contiguously available, or two chunks of bandwidth that are not contiguously available, operator has to configure two different bandwidth part, and the user cannot get more than 10 megahertz even if the base station decides to allocate. So this is a kind of a disadvantage in case if the operator doesn't have contiguous chunk of channel bandwidth available because of the limitation of supporting only one bandwidth part in downlink and also one bandwidth part in uplink simultaneously if you are talking about using FDT kind of system. Is that clear to all of you? So let me show you the example of bandwidth part in the context of mixed numerologies. Look at the illustration. It is again time frequency axis where you can see clearly we have three different bandwidth parts. The first one is with numerology 1, the second one is with numerology 0. Oops. Yeah. And the third bandwidth part is designed or configured with numerology 2. So look at the base station point of view. At the base station, all these bandwidth parts are configured and the base station is able to serve using these three bandwidth parts simultaneously to the respective users. But if you look at user point of view, we have user set 1, user set 2, and user set 3. So if you assume that we have certain number of users in the network. So user cannot be part of these three numerologies simultaneously because user can be part of only one bandwidth part at a time. And in this example, I am showing you the bandwidth part in a quite simplistic manner. If you look at, I am showing you only one resource block of 14 symbols as you see here. This is also one resource block, This is also one resource block of 12 subcarriers in the frequency domain and 14 symbols in the time domain. Okay, anyway, we cannot define time domain. In time domain for a resource block, it is, okay, I would say, no, I think you should not say it is one resource block. In LTE, it is correct. Do you all agree with me? I think I'm wrong. So let me repeat. So look at in the frequency domain, how many I have here? Oops, I think I'm correct only. So I was confused between time. I thought this is the time and this is the frequency. It's not correct. What I said is correct. Are you following what I'm trying to say? Here in the time domain, if you look at here, in the frequency domain, here I'm showing you only 12 subcarriers. Here there are 12 subcarriers. Here also, if you really count, there are 12 subcarriers. Here also there are 12 subcarriers because as you go from numerology 0 to 1, the width of the subcarrier spacing is doubling. And it is more clearly visible when you look at the numerology 2. But otherwise, the number of subcarriers that I have in the frequency domain are 12 only. Because of that, I have one resource block here, and even I have only one resource block here.
Yes, sir.
Right? All of you agree with me? So in the frequency domain, I have only 12 subcarriers. So if you have, let's say, another, then I would say that I have two subcarriers, two reserve blocks, each with the 12 subcarriers kind of thing. But anyway, I cannot do that kind of thing. Ideally, I should have done something like this. Right?
Yes, sir.
So in this case, I have another 12 subcarriers. So together, I would say that I have two resource blocks using numerology 2. And in this case, with the numerology 1, I have only one resource block, and with the numerology 0 also, I have only one resource block.
Sir, for a particular bandwidth can only follow one certain numerology, right? And if it
Look
does
at
not
look
want
at
to,
look at here this illustration, the third case.
yes, yes. So if it does not want, then it has to do bandwidth parting and it has to divide itself into two bandwidth parts and then they can follow different numerologies.
No, no, I didn't get Suranjan. What you are trying to say with respect to this figure?
I'm saying that two bandwidth parts can have two different numerologies, right? Like last, just like the diagram we just
Ye-
seen.
Yes, here I have three different bandwidth parts, each of them with their respective numerologies. Yes, you are right.
Yes, so let's say I have one bandwidth of say 200 gigahertz or something like that, 200 megahertz or something like that. So if I want to have three different numerologies in that particular bandwidth, I cannot have it just like that. I have to divide that bandwidth into three parts and then I can assign three different numerologies.
Yes, yes, yeah, you are right. You are right. If you want to have different numerologies, yes, as simple as that, you divide into three parts and you start assigning. Yes,
Right, sir.
right, right. But the this case three is not that one. The case three, if you look at very carefully, it, bandwidth part two is subset of bandwidth part one. This
Yes, yes.
so what you are talking about is, I think, the case like two, where I am dividing my carrier bandwidth into two parts, and I can put numerology one here and numerology zero here. And if this is also available, I can put, let's say, numerology two here. That is the case that you are talking about, right?
Yes, sir. Yes.
Okay, so the point I was trying to say that this is a simple example showing only 12 subcarriers for each of the bandwidth part in the frequency domain, but in practice, we'll have multiple of such resource blocks allocated for each of the bandwidth part. And this example is talking about how a given user can be dynamically adapting the configured bandwidth. I mean, dynamically choosing one of the sorry, configured bandwidth parts. As I was mentioning, there are four bandwidth parts that can be configured, and out of four, only one at a time is active. So this is an example showing there are two bandwidth parts. One is wide band and other one is narrow band. Initially, the user is using the bandwidth part one, which is narrow one. After a while, using this PDCCH or even the RRC messages, dedicated RRC messages, the base station can inform the user that, okay, from this time interval onwards or from this slot onwards, let's say slot X, you can start using the bandwidth part 2, which is having more number of reso blocks in the frequency domain, and also it can inform the time duration also. After that, again, it can come back to the initial bandwidth part. So like that, it can be dynamically adjusted on per UV basis depending on the logic that you have at the base station. So is it okay to all of you what I was trying to say? I have only a few slides explaining what is bandwidth part and what are its various use cases, how a given user can dynamically adapt its bandwidth part based on the instructions coming from the base station. So if there are no queries, I will move on to the next topic. So that is the time domain structure. So we have seen so far the frequency domain structure where we looked at different numerologies followed by bandwidth part. And more or less, we have seen how things look like even in the case of time domain structure, except that I didn't show you earlier the top part of this illustration where we take 10 subframes together. If you look at here, each subframe here is of 1 millisecond, where we are taking 10 such subframes together, which is equal to 10 millisecond in the time domain. and we are calling it as frame I. So in the time axis, if you see that we have different frames. I was mentioning about we have these frame numbers varying from 0 to 1023 and getting wrapped up. So like that we have frame I plus 1, so on, going on forever in the time domain. And if you peek inside any given frame, it comprises of 12, sorry, not 12, 10 subframes, each of 1 millisecond. And if you peek inside one subframe, if it is subcarrier spacing 15, it has only one slot of 14 symbols. If you go to subcarrier spacing 30, it has two slots, each of 14 symbols. If we go to the subcarrier spacing 120, that is the numerology 3, which is supported in a millimeter wave only, where we have one subframe of 1 millisecond having 8 slots of each 125 microseconds, each having 12 symbols inside it. That is what being shown here. If you peek inside any of these slots, it contains symbol 02, symbol 13. So is this part clear to all of you? So I will talk about mini slot once you understand this concept. So what is frame, what is subframe, what is slot, and how they are varying with respect to given numerology. So if you see what is varying with respect to numerology very carefully, what is varying is the subcarrier spacing. The effect of the subcarrier spacing is the number of slots in a given subframe, or you can also say that number of slots in a given frame. Is this part clear?
Yes, sir.
And also look at these points. This structure of a frame containing 10 subframes is fixed. It is numerology independent. And the subcarrier spacing and the number of slots that you can get in a given subframe is highly sensitive to the subcarrier spacing or the numerology that you use it. Okay. And also finally, if you look at inside a slot, the number of symbols that you have, they are also fixed. Okay. Now look at the case where uh, you have the choice of using any of these four numerology that you see, and assume that you wanted to reduce your end-to-end latency for the applications, or the average latency that is your application is going to experience. So which numerology you may configure out of these four choices that you have?
The three one, the numerology 3.
So how it is going to help you in reducing the latency?
Because we are packing more symbols in 1 millisecond or one frame, whatever you say.
You are packing more symbols in
In a particular time period.
or
Like say in 1 millisecond subframe for numerology 0, we are only packing this 14 symbols.
but if you look at 1 millisecond level, and if you calculate the resource elements, do they change widely across these numerologies? If you take one subframe of 1 millisecond and you are asked to calculate the number of resource elements, you have done it yesterday also.
Yes, sir.
And do you think they vary widely as you go from one numerology to the next numerology?
So I think yes, sir, because we are here. We can see now that there are more, like in numerology 1, we have more slots. Like we have slot 0 and slot 1, and each slot can hold 14 symbols. So we are sending more symbols. So
What about others? See, what I'm asking is very simple. Take this case of having 30 kilohertz. Oh, sorry, not 30 kilohertz. I would say, say we have the bandwidth. I think yesterday we have taken the case where, right, the bandwidth of 20 megahertz. And if you take numerology 0 and numerology 1, So how many reserve blocks that we got? So this is 106 and this is 51, right?
Yes, sir.
And if you calculated the resource elements over a time span of 1 millisecond. Okay, let me write this left hand side. We are calculating the resource elements. So how many will get here for the numerology 0? It is 106 into how many?
Into 12.
12. It is in the frequency domain and in the time domain
14.
14.
14.
14 into what is it? You are saying something else.
No, sir, this is it.
Wait.
That's it, right? So
Yes.
Yes, sir.
these are the subcarriers and in the frequency domain and in the these are the symbols in the time domain. So multiplication of these two will give you the number of resource elements. And here if you come to the right side for the numerology 1, it is 51 and into 12.
12.
These two are in the frequency domain. And in the time domain, we have 14 into 2. So approximately they are the same, right? Of course, there is a minute difference because the way you are packing the things in the frequency domain, and it is not 106 divided into half. It is not 53 here. It is not 53 because of that. Uh, so this guy is slightly, sorry, opposite, right? Yeah, this guy is slightly higher than that one in terms of the resource element, but it is a marginal difference, not so much difference. But I was asking about the case where you wanted to reduce the average packet latency. Which numerology out of these two that you pick? In other words, what I'm trying to say is the channel capacity that you get R1 or R2 if you call it as. Of course, R1 is greater than R2, but the difference of R1 minus R2 is not so big. So ignore this part. For a while, assume that R1 equal to R2 because they are more or less equal. So what I'm asking is which numerology is better for reducing the latency?
Sir, for higher numerologies, the scheduling decisions can be taken like much more flexibly. So, like, can
Yes. Yes, you are right. You are coming closer. Yeah, because you can take scheduling decision quite faster. Here, numerology 1 take the scheduling decision 2 times in the time span of where the numerology 1 is taking one scheduling decision, right?
yes,
And also we say all the time the internet traffic is bursty in nature, right? And because of all this, what could actually happen is if you have the ability to serve the traffic that is waiting in the queue, like at the end of the day, what you are talking about is we have some traffic that is waiting in the queues for different users. But whether it's a downlink or uplink, doesn't matter. So now tell me the average queuing delay between numerology 0 and 1. So which one do you think will have less queuing delay? As you see, the channel capacity is more or less the same. Which one will have less queuing delay?
Numerology 0. One would have less queuing delay compared to 1.
Numerology 0 or 1? I thought you would say 1, but you said exactly the opposite. Why numerology 0, which is doing the scheduling decision once every 1 millisecond, here the TTA is 1 millisecond. Here the TTA is 500 microseconds. Is not clear what I'm trying to say? Here, the waiting time in the queue when you go to the numerology 1 will be reduced because now you are able to go and start serving the queue 2 times while other guy is serving the queue 1 time. So that is the average waiting time in the queue reduces as you go to the higher and higher numerologies. That is the kind of helping when you have ultra low latency applications. Is that convincing, or you didn't get convinced about this intuitive way of how higher numerologies are kind of
So,
reducing
the capacity is almost same, but the rate at which we change the scheduling decisions is basically the factor here.
Yes, yes, yes. The rate at which you are doing the scheduling is faster. Because of that, you are not actually leading to the higher queuing delay for the packet that are waiting in the queue. And also again, as you see here, higher numerologies, even though they have a little bit lesser capacity, you can say that the latency that packets will experience can be quite significantly reduced as you go for higher numerologies. This is especially important during the congestion situation. So especially during the congestion, what happens? Your latency goes for a toss. It goes quite high. But when the network is highly loaded, when you are doing this kind of a micro granular scheduling, it can help you to reducing the latency quite significantly compared to the other case of doing the things at only 1 millisecond. You can try out this case in the NS3 assignment that I have given. In fact, I have asked a couple of questions related to this part as well. I want you to really conduct experiment and comment and also see why it is indeed the case. Okay. Okay. So let me come back here. So I was showing you here multiple numerologies, and I was just mentioning about higher numerologies are the one that are recommended when you have these low latency applications in your network. But some operator uh, got certain channel bandwidth, and for whatever the reasons, they cannot able to use higher numerologies. So they decided go with only numerology 0. But they have to support some ultra low latency. See, I'm not putting ultra reliability here because ultra reliability is not something that you can get here. That you can get using hybrid IRQ and AM mode in the RLC layer and other thing. Here, the latency can be reduced by choosing the appropriate numerologies. I'm saying using higher numerologies, you can able to reduce the latency for the packets. That is okay. But if it is not possible for you to choose higher numerology for your base station, what is the thing that you can do? That is what the mini slot comes into picture. So in 5G, the scheduling is done every slot. So the base station does the scheduling for this slot. In this case, it is 125 microseconds. Not 5. No, not 125. No, this is not 250 actually. Yeah. Here it is 125 microseconds. This is 500. So these are the TTIs, scheduling time intervals. Transmission time interval it is called. So this is nothing but your scheduling interval. So when you take the numerology 0, we are doing the scheduling once every millisecond. And when you go to the numerology 3, you are doing it once every 125 microseconds. That way it is doing in 1/8 of the time of numerology 0. But you want to support URLC application or ultra low latency applications, ultra low latency application. In the case of numerology 0, you can do something called mini slot, where you can do the scheduling at symbol level. So far, I was showing you about slot level scheduling at 1 millisecond, 500 microsecond, 250 microsecond, and 125 microseconds. But when you take this particular numerology, where the scheduling does happen at 1 millisecond, we can actually do something at symbol level scheduling using something called mini slot scheduling, where it is possible to allot 2 symbols or 4 symbols or even 7 symbols out of the 14 symbols in the slot for the numerology 0 to ultra low latency application. What does that mean? Here at a time, let's assume that time t equal to 0, the base station can decide that this slot of 14 symbols can be allocated to different users, something of that kind. But after a while, if you start experiencing the traffic of low latency applications coming, they have to wait for next 1 millisecond interval to arrive before their traffic gets served. And for some applications, yeah, that much of the waiting time is also quite costly. To reduce this waiting time in the queue, we can introduce this symbol level scheduling. That's what you can see it here, where the scheduler can also preempt the existing allocation of the resources to the other users and other applications and dynamically inform, again using this PDCCH. You can use the PDCCH to tell that, okay, starting from the symbol 4, I'm allocating these 7 symbols for certain users for your LLC. Like that, we can allocate 7 or 4 or 2. That way, we can support mini slots even when we have these lower numerologies with lower subcarrier spacing. It's not that you have to always go for higher numerologies to support low latency applications. So that is the point here. We have both the choices. Let me talk about duplexing schemes. So at a high level, I guess all of you know about duplexing. We have seen TTD and FDD earlier when I was talking about the cordless phones. And FDD we looked at in the case of GSM. So I hope all of you remember that part, where in the case of cordless phones, we use one channel. They work on ISM band, which is unlicensed, where you allocate certain time slots in the TDMA frame for downlink, certain time slot in uplink. That's what we have done in cordless phones. In the GSM, what we do for a given handset, whenever you are making voice call or when you are receiving voice call, you allocate one uplink frequency and one downlink frequency, which are separated by a certain chord band to avoid this cross channel interference. So this is the TDD and FDD. And we have another variant of FDD that is called off-duplex FDD. So in fact, maybe I should say that your GSM phone actually comes here actually. I mean the 2G phones, because so what is the meaning of full duplex FDD is, this is called full duplex. So this requires 2 RF chains at 5 layer. Whereas here we can manage with 1 RF chain, so that we can reduce the cost of the handset. So what happens is, yes, we use one uplink frequency and one downlink frequency, but we don't be using both of them simultaneously. So you can see that they're kind of spread across in the time domain, and they are not overlapping in the time domain. Of course, we can also do other case where you don't do any division in the time domain and frequency domain, but this is for future studies. Still, 3GPP is exploring to include in the advanced version of the 5G or in upcoming 6G cases. But as of now, 5G supports these 3 duplexing schemes. One is the TTD. And also, if I ask you, can somebody tell me, is the TTD is full duplex or half duplex? This one. Can you classify this TTD as full duplex or half duplex?
Sir, half duplex.
Half
Right?
duplex.
So we don't have the choice of full duplex in the case of TDD. It is always half duplex. So it is taken for granted. Whereas in the case of FDD, yes, we have both the choice of full duplex or half duplex. In all the cases, base station is always full duplex. We don't want to save anything at the base station after doing all the investment in setting up the base stations and trying to get some revenue out of that. But it is all at the user side where you're talking about half duplex FTT and other things. So we have something called a slot format where we indicate out of the 14 symbols within a given slot how they can be used. Look at the right hand side illustration. What I'm showing here are the like 14 symbols. In a slot. So that way, irrespective of the numerology, what I'm telling you is valid. So if you take a slot of 14 symbols, so I'm showing you some sample configuration of the symbols for downlink, uplink, and other cases. If you look at the first one, what I'm showing is that out of 14 symbols, all the symbols are used for downlink. The second one is where all the 14 symbols in a given slot are used for uplink. So that way you see clearly if it is FDD, where we have one for downlink, one uplink, and one downlink. So my slot configuration has to be in other words, it is by default. You don't have to do anything. So what I'm trying to say that in the case of FDD, where you take one carrier frequency for downlink and one carrier frequency for uplink, all the symbols in the given slot are always used for downlink and uplink respectively. I hope this point is clear to all of you. So that way FTD is a kind of a very simpler thing to understand and also simpler thing to design because we use separate carrier frequencies with the guard band and filters so that we take care of multiple things easily. But even in the case of 4G as well, we have both FDD version of the 4G and even the TDD version of the 4G. And it is so popular, the TDD version over the FDD version. The reason why the TDD version is more popular is you can look at the remaining configurations of slots, or not the slots, remaining configuration of the symbols in this illustration, where in a given slot, I can mix and match, where out of 14 symbols, some I can allocate for downlink and some I can allocate for uplink. That way, I can get lots of flexibility in the way I can use these symbols depending on the logic that I have at the base stations and depending on the nature of the traffic that base station wanted to serve. That freedom you don't get with FDD. FDD, once I decide that, okay, this is my downlink channel bandwidth and this is uplink channel bandwidth, you figure it out how many receive blocks will be coming in downlink and uplink. All the receive blocks in the downlink will be always available for downlink transmissions. All of them will be available for uplink transmission. When the traffic is bursty and where sometimes there is more traffic in uplink compared to the downlink, you cannot do anything in the case of FDD. That is the kind of a problem that you can see with FDD, which is a kind of insensitive to the traffic fluctuations or variations and may not able to meet all the kind of guarantees that you expect for different applications. But all different configurations that you see here in this illustration, except the top two, are the one quite interesting for TDD. Having said that, even in the case of TDD, I can use this configuration and this configuration. Nobody prevents a base station where it is having one channel bandwidth to use all the slots, all the symbols. Again, I'm confusing between slots and symbol. But in this slide, I will come to the slot level next slide. But in this slide, all of them are symbols. Where when I have 0 to 13, I can have multiple different ways. Some symbols in a given slot can be used for downlink and uplink, including the first two configurations where I can configure all of them for downlink or all of them for uplink. That you won't be doing it because sometimes with real-time traffic and URLs traffic and reliable traffic, you want to get the acknowledgement. When you want to get acknowledgement, at least you should have something like this. Look at this case. What is this meaning of that is, out of 14 symbols, in this case, 11 symbols are configured for downlink and one symbol is configured for uplink. And there are two symbols which are shown with dash. These are called flexible. These are flexible symbols which can be used for downlink or uplink, or they can use to create something called guard period. Okay, so this guard period is important in the context of TTD. It is used for two main purposes. One of the things why we need to have this guard period is, take this particular example. Maybe I will use a small animation here. So this is the base station, and so this is the user equipment. And I'm talking about using a TTD where we use, where we do both downlink and uplink on same channel. And if my configuration is something like this. So what is the kind of what I'm trying to show here is, this is the case where the base station is serving in downlink using these three symbols, and the basically it is like a downlink traffic. And this is where let's assume that this is a kind of a TCP traffic and downlink TCP traffic, where the user equipment wanted to give acknowledgement. Again, I'm talking at the TCP level, but even if you look at hybrid ARQ, the hybrid ARQ which is running at the MAC layer, if you recall, I was talking about getting ACK or NAC using physical uplink control channel. So I can use this symbol to realize the physical uplink control channel, and I can give the acknowledgement for the downlink data within the same slot itself. That means if I assume my slot equal to 500 microseconds, I'm not only transmitting the data from the base station to the user where I'm sending the data, user is also sending the ACK, at least at the MAC layer. In this case, I'm talking to the base station. All these are happening within 500 microseconds. So that is the beauty of TTD, where you can configure the symbols for both downlink and uplink, including some special symbols which are called flexible, which can be dynamically decided to be configured for downlink or uplink or for guard period. So let me explain you why I need the guard period. Then I will explain flexibility of these symbols for downlink and uplink in the following threads. Let me see why I may need to use this to create something called guard period. Take this case where data is coming from the base station. So now tell me, base station is in the TX mode. And what about the handset? Which mode it is there while the data is coming to the user equipment? The handset, which is in what mode?
RX
RX mode. For sending acknowledgement, the handset has to be
in TX mode and base station has to be RX mode.
Right? So it takes, as you see here, like in this example, I'm showing there are three symbols. At the end of the three symbols, the user equipment A has received the data, and in the fifth symbol, it wants to send the data. I mean, it wants to send the acknowledgement. So it take certain non-negligible amount of the time for doing two activities. One is it has to process the data that it has received and prepare the acknowledgement. That's what happens at the MAC layer. Not only that, it has to switch from reception mode to the transmission mode, which typically takes 20 microseconds. To switch the radio from TX to RX or from RX to TX, it will take typically 20 microseconds. So for that reason, we have to keep guard period. So this is something that is specific to TTD because we are using the same channel for downlink and uplink. We need to create guard period. Basically, in the process, we are actually losing some symbols in the time domain. But it is a kind of overhead, but we are kind of ready to accept this overhead because it kind of helps in creating a lot of flexibility in the way you schedule in downlink and uplink. Is that point clear to all of you? Why I'm saying we have these flexible symbols which could be used as guard periods. And another reason why we have the guard period, apart from so this is one reason, and other reason why we have the guard period is something called timing advance. So maybe I may not go deep into this, but the idea behind this is very simple. Maybe I'll give a toy example. Let's assume that there are two students. One of them is commuting from hostel, and other one is commuting from the city, and we have meeting at 11 o'clock in the campus. And tell me who has to start first, from his home or from his room?
The one living in city.
So that is what timing advance is about. So when you take a base station, and I have one user who is very close by, and one user is at the cell edge, let's say he is at 3 kilometers away from the base station, and he is at 100 meters. And I'm talking about using TDMA structure, TDD mode. So let's say that let me also name the users, and this is user A and user B, and the base station has decided to give slot A and slot B. Sorry, yeah, slot 0, slot 1. Okay. So what happens? Look at here. So like this is the time domain. Okay, this is the time. So slot 0 is given to the user A, and slot 1 is given to the user B. And if you calculate the propagation delay, the propagation delay from A to the base station is kind of 0, right? But when you have 3 kilometers, 3 into 10 to the power of 8, right? So how much you will get? It is 10 to the power of minus 5, isn't it?
Yes, sir.
So 10 microseconds. While for this guy, it is, you can always treat it like almost 0. Whereas for that, it will take 10 microseconds for the data to arrive. And also I was telling about this cyclic prefix other day. So that also is designed by keeping in mind the size of the cell. So can somebody tell me for numerology 0 versus numerology 3, which of them will have higher cyclic prefix?
Zero.
So if you recall, here the spacing in the frequency domain, okay, maybe I'll write down again here. Here it is small in frequency domain. And the time domain, we have, I think, 67 microseconds or something, which is high. And as you go to the numerology 3, so it is 120. And this is high. And in the time domain, so you have to divide this by 8. So what is this? What I wrote here is the symbol duration. That's the reason why we have 8 slots in 1 millisecond in numerology 3. Am I right? What I'm trying to say here? So here what happens is when you want to create macro cells which supposed to cover a lot of distance, then what you do is you want to also factor in for the higher propagation delay. As you see here, the propagation delay is higher. So that has to be also factored in the cyclic prefix. That's the reason why when the cell size is larger, we should have higher cyclic prefix. That's the reason why we'll be using the numerology 0 and 1 in those kind of situations. And for small cells, where you have only 100 meters maximum between the sender and receiver, in this case base station and the user, the propagation delay is same for all the users in the cell because it's a small cell. Then you don't really have larger cyclic prefix to account for the additional propagation delay for the users which are from further away. So because in this case, if I come back to timing advance, because this user has the propagation delay of basically it is like a travel time. If you look at the example that I was talking about, there a student who is staying in the city is commuting, means he has more travel time. So he has to start maybe at 10 o'clock for the meeting at 11 o'clock. So that is the propagation delay in this case. Whereas for those who are staying in the hostel, they have to start only 10 minutes before the class. So if you look at in the time domain, this guy started at t equal to 10:50, and this user started at t equal to 10. Even though, take this example where, let me simplify the case where I have 2 users and the base station has decided to allot this slot. This particular slot. This is the slot that is allocated. If this slot is allocated, and let's say this is the slot, not the slot, in this case, I think this is the symbol I'm talking about. But anyway, each symbol will take certain amount of the time. Okay. So if this is a symbol that is allocated, and if I'm talking about user A can start transmitting just, let's say if I call it as a T, so you can start transmitting at T minus delta. So that the transmission from A will reach the base station in exactly in this interval and follow it. But if I take this user, he has to start at T minus 10 microseconds. So that by the time the signal will reach the base station, it will fall within this particular time slot that is allocated or the symbol that is allocated to the user. So that's the reason why we use the guard bands. One is for switching between TX to RX, and other one is to account for timing advance, which is extremely important as the cell size grows higher for macro cells, to account for the propagation delay for the cell edge users. Again, you don't have to worry, I'm not going much into what is timing advance and other thing, but they really play a lot of role in kind of ensuring that the data of different users should not be overlapping in the time domain by the time they reach at the base station. That is the point. Okay, so I think these are all the points that are talking about. If you look at slash, they can be used for downlink and uplink, and also can be for the guard period. These are necessary for TDD for switching from downlink to uplink, and also to account for timing advance. And let's look at how this scheduling is done in the case of TTD. We have actually three different configurations of the slots in TTD. One is static, other one is semi-static, and the last one is the dynamic. The control information related to static and semi-static can be conveyed to the users using RRC messages. Whereas the dynamic scheduling information of the slots for downlink and uplink can be conveyed using physical downlink control channel. And in the case of FDT, as I was just mentioning, on a given carrier frequency, all of them are downlink and or uplink for all the time. So let me show you how TTD configuration looks like in the case of 4G. So what you see is a TDMA frame in the case of 4G. If you look at the high level, even in the 4G, we have the frame of 10 millisecond, which is divided into 10 subframes, each of 1 millisecond. That is exactly what we also following even in the case of IGNR. Okay, and in the case of TTD, what you see here is the base station can configure the cell. The base station can configure the cell to be operating on one of these 7 downlink uplink configurations. Where here the illustration that you see here I am talking the things at the subframe level. I'm not talking at the slot level. I'm not talking at the symbol level. I'm showing the things at the subframe level. In other words, at every 1 millisecond, I'm saying, if you look at in this case, I'm saying that out of 10 subframe that I have in the case of configuration 0, and the first one is for downlink. The second one is a kind of a special subframe which has a mix of both downlink and uplink. And then we have second one, third one, and fourth one, which are meant for downlink. Then we have fifth one for uplink, and we have special subframe. Then we have seventh, eighth, and ninth, which are meant for uplink. So these are all at 1 millisecond granularity, which contains again 14 symbols in each of these subframes. So like that, depending on whether you have more downlink traffic or uplink traffic, we can configure a base station to use one of these 7 configurations. And also very often what it is, the neighboring base stations also will be configured with the same configuration of your base station, so that there may not be cross base station interference or inter-cell interference, especially for the cell edge users. Again, you can see there's a guard period that is defined to take care of the timing advance in the case of TDD here too. So let me show you how these configurations are different in the case of 5G compared to what you see in the case of 4G. Again, repeat here. I'm saying that in the 4G, the configuration of a subframe is either downlink or uplink, and there are 7 such configurations that are defined, which kind of stay for, let's say, hundreds of frames. For the next 100 frames, maybe a base station can say that I am using configuration 0. Then it can decide that, okay, for the next 200 subframes, for next 200 frames, where each of them is 10 millisecond, I am using configuration 3. Like that, dynamically it can change depending on how the traffic in the cell is varying. Let's look at slot configurations in the case of 5G. We can use these RRC messages to inform the slot configuration. And there are 2 kinds of RRC messages that you can use. One is related to the configuration common. Read this word, something called configuration common. As the name says, here we are kind of telling to all the users in the network what is the slot configuration of this TTD cell. And this example is something simpler to understand. And I'm talking about this one pattern in this example. What is the meaning of pattern is the slot configuration that is valid across multiple slots. That means I take multiple slots and decide which slot should be for downlink or uplink. What I'm showing here is across multiple slot is analogous to what I'm showing you here in this slide for 4G at the subframe level. Because if you take numerology 0, Is subframe here is equal to slot in the case of 5G. So the pattern is nothing but the configuration of slots or the subframes for certain amount of the time. So look at the illustration. I guess you should be able to easily understand. Before looking at the illustration, look at okay, maybe start with the illustration itself. But for you to understand illustration, we have something called slot configuration period. That means the length of the time for which this slot configuration is valid. In this case, it is valid for 2.5 milliseconds, which is equal to 20 slots. That means base station is telling to all the users, for the next 20 slots, I'm going to have this configuration of slots for downlink and uplink. That is the meaning of this. Where it is saying that out of, if you look at 20 slots, it is saying that this 7, like the number of downlink slots, it is saying that these 7 are for downlink, and it is saying that these 4 are for uplink, and the remaining one that you see it here, these are all flexible. That means they can be used for downlink or uplink. Then we have 2 special things where you can see that if you open inside this, it has a combination of downlink and flexible. That see here, what I'm showing is this is at the slot level. Slot which contains 14 symbols. And when you peek inside a given slot, there you see 14 symbols. Here what you are saying is, in a given set of 14 symbols which are part of one slot, how the symbols can be used for downlink or uplink. So in this case, what is being shown is the next 2 parameters that you see it here. It is saying that the number of symbols that are used for downlink are 4 in a given slot, and the number of symbols that are used for uplink are 7. So is this clear to you guys, what I'm trying to show here? So try to look at the illustration. So let me know if you don't follow any of this.
So this is one subframe, right? Like what we are seeing as DDD, FFF, and UU.
Which one? The top illustration or the bottom one?
This one, like DDD, then DF, FFF, FU, and UU.
No, no. So this is over a span of 20 slots.
Okay, so
This is slot 0. Okay, unfortunately, slot and symbol both got same prefix. Okay, this is slot 0. Each of them is a slot.
okay,
Whereas here, each of them is a.
yeah, that is symbol. That's fine.
What I'm saying is, at the base station, I'm saying that if you look at the 12 slots in the case of TTD, see in the what is the beauty of the TTD is I can use a slot for downlink or uplink, right? I have only one carrier. I can use a given slot for downlink or uplink, right?
Yes, sir. Yes, yes.
So what
I
I'm
got it.
showing is if I take a configuration of 20 slots for the next 20 slots time interval, how I can configure the 20 slot as a combination of downlink slots, uplink slots, flexible slots, and special slots. When you look at the special slots, you can see that we can have a mix of both downlink and flexible inside these special slots. That also being shown here. Okay. Okay, sorry. I think this 7 that you see it here should go here. So when you say here, what I'm saying is when you look at this special slot, which is a combination of both downlink symbols and flexible symbols, 4 symbols are meant for downlink, and these 7 symbols are still flexible. That means they can be further decided later time for downlink or uplink. And this 7 here says that this special subframe contains 7 uplink symbols, and it contains 3 flexible symbols. So they can be decided later stage for downlink and uplink. So why we still have flexibility even after doing all that? Look at here. I'm talking this only for these two, but still if you look at this 1, 2, 3, 4, 5, 6, 7, these 7 slots are still flexible. They are not decided at this stage, therefore downlink or uplink. So what happens is at the macro level, base station is informing the users that I am going to have this configuration of 20 slots, where some of them are for downlink, some of them are for uplink. For other thing, it is saying that I have not yet decided. I will decide at a later stage during the respective slots. That is the meaning of this. And if this is a case of having a single pattern, where pattern is consisting of 20 slots, where I will repeat the same pattern again and again. So for these 20 slots, this one, and again for the next 20 slot, I can use this one, or if you want, you can go with something else. Then you have a separate case where the base station is configured with the 2 patterns. Look at the illustration again. And this whole thing will get repeated after a while. So here what happens is, this thing will get repeated after 2.5 milliseconds, where in this case, the combination of pattern 1 and pattern 2. What is pattern 1 and pattern 2? You can look at here. Pattern 1 has certain combination of downlink, flexible and uplink. And inside this, it has certain pattern of downlink and flexible symbols. And if you look at pattern 2, you can see that it has less downlink than the pattern 1. And it has more uplink than the pattern 1. And if you look at the flexible slots, then it has a combination of downlink and uplink kind of thing. So where this is a frequency at which, frequency means, don't confuse with the frequency there. So it is the period at which these patterns are again repeated in the time domain, so that users are aware of which slots are for downlink and which slots are for uplink in advance. And if at all you have some power save users, if they don't have any traffic to transmit, and if they're not expecting anything, they can simply go and sleep till the time they want to sleep. Then we have second variant, where the flexible slots or symbol that you see it here in the previous case can be assigned at a later stage for the dedicated users using the configuration dedicated. So look at here. This is the previous example that I was showing you using the configuration common. Then see what is done with configuration dedicated. Before talking about configuration dedicated, let's relook at what is done in the case of configuration common. What I am showing you here is, again, I have 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, so again, these are the 20 slots, same example. And these slots are for downlink, these slots are for uplink. These are the 2 special slots, and these are all flexible, which are not yet allocated. That means the base station has not decided at this time how to use this flexible slot, whether for downlink or uplink. That's what done. But later, using these RRC messages again, now these are like a dedicated RRC messages. These are meant for specific users. The base station is now telling to the user that how these slots can be used by the user. Look at here. Now, if you look at, it is saying that these even though initially said that this is downlink and flexible, it is a combination of D, 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 and F. It decided that this should be completely downlink. That's what called all downlink. This is flexible, but it is decided that even though I can have a mix of both downlink and uplink, all the 14 symbols in this F slot, it decided to give all the 14 symbols for downlink only. Is that clear? What I am trying to show here? So for downlink, which was decided as part of the configuration common, there's nothing that you can do at a later stage. The fate of these slots is frozen for the next periodicity of these 20 slots. Similarly, the uplink slots, whichever that you see it here, is frozen. Only we have to talk about the slots that are marked as D/F or F or as F/U, because they contain flexible slots, they contain flexible symbols inside flexible slots. So you have to specify whether they should be for downlink or uplink. So in this case, I'm saying that this special slot has been decided to be used exclusively for downlink using configuration dedicated. This flexible slot also is decided to be used as downlink only. And interestingly, this flexible slot is decided to be used for downlink and flexible. So as you see here, still some uncertainty is left here. And these were not given for any user. These are not configured for the user. That is the meaning of this. Similarly, you can see that this is configured exclusively for all uplink. So like that, the base station can decide the things over a transmission periodicity of 20 slots or whatever it is, where it decides some as downlink, some as uplink, some as flexible. And when the time actually comes as part of the TTIs, transmission time interval, that is a scheduling interval, it can actually decide the fate of the flexible slots and even the flexible symbols inside slots, where it may not have to configure all of them for the given user, because these are for UV specific things. Okay, so last couple of slides for today's class. This I was showing you even in the beginning of today's class as well. We have something called self-contained slots in 5G. The remarkable feature of these self-contained slots, this is again is important in the case of TDD only, is because all these are applicable for TDD. The TDD is highly encouraged in the case of 5G. Look at here. What I'm showing it here is TTD downlink and TTD uplink. So if you look at the first part, the first one, what you see here is we have this downlink control information that is coming. That is what the PDCCH, which contains the DCI. So that's what even being shown here in the bottom as well. If I take two slots, this is an example showing two slots, okay? And this is example showing you one slot. A slot contains in the beginning the DCI, and one major difference between a PDCH that you have in 5G and 4G is in 4G, occupies entire bandwidth in frequency domain. Whereas in the case of 5G, if I have, let's say, these are my resource blocks, and I can assign a subset of, let's say two bandwidth parts, one and bandwidth part 2, and inside each bandwidth part I can only have certain subset of things in the frequency domain for PDCH. In other words, the PDCH in 5G doesn't occupy the entire bandwidth in the frequency domain. It occupies only a part of that. So that is a major difference. So anyway, what I was trying to show here is the first one that you see here is uplink heavy configuration. Something is similar to here, like something like this. These kind of things, where the most of the symbols are allocated for uplink, and one symbol in this case is allocated for downlink, and there are some flexible symbols as well. This is in the case of a slot. Slot is nothing but 14 symbols. Okay. Depending on the numerology, they occupy 1 milliseconds to 125 microseconds. So what I'm showing is also here at the slot level, and for timing, it will assume that slot equal to 1 millisecond for numerology 0. I'm showing you the top one is the uplink heavy configuration, where you convey in PDCH that, okay, whatever the cell specific control information. Then we have some guard band. As you see, we need guard period for the user to switch from reception mode to the transmission mode. At this time, during this time, so let's assume that this is one symbol time. During this symbol duration, your handset has to be there in the downlink. Then there is certain guard period for your handset to switch from downlink to, so I mean, from the reception mode to the transmission mode. Then the handset can start using these symbols to transmit the data, and it also can send any control messages, like it can send that what is that, buffer status reports, the power headroom, and etc. It can send using the control messages. This is nothing but your the PUCCH, physical uplink control channel. This is in the case of uplink heavy slot. And look at the second example, which is exactly the opposite, which is the downlink heavy. Again, we have PDCH as part of the downlink control symbol. Then the rest of the symbols are used, except the last one or last couple of one, for downlink, for serving the users. Then we have the guard period, so that if the same user you are expecting to send acknowledgement within the same slot, the user has to receive during these symbols. Then during the guard period, he can switch from reception to the transmission, and also prepare the acknowledgement and send HARK packet and other things. So these are the things that really helps 5G to be able to support extremely low latency application, which was not possible even in the 4G, and even in Wi-Fi also we don't get this kind of thing. There is several milliseconds before you transmit in downlink and receive acknowledgement in uplink, whether it is 4G or even whether it's Wi-Fi. But in 5G, as you see here, if it is 1 millisecond, within 1 millisecond, you are sending the data to the user and getting acknowledgement from the user. And if it is 125 microsecond, in the case of numerology 3, again, within 125 microseconds, you are sending the data to the users and getting acknowledgement from the user in terms of ACKs or NAC. Of course, we are talking about sending TCP ACKs, which comes under application payload. Then the user can make a request to the base station using PUCCH or other modes, and the user can be served in the upcoming thing. And if you are doing the scheduling at every 500 microseconds or even 250 microseconds, the acknowledgement TCP/ACKs from the user will be coming much faster rate compared to what we have in the 4G and even in the case of Wi-Fi. So these self-contained slots are also quite powerful, and they help 5G to realize various time-critical applications. The last slide for today is showing the relationship between the cell size, the end-to-end latency, the carrier frequency that you are using. So look at the illustration and try to appreciate why the figure looks like this. And if you have any questions, we can discuss.
So this frequency is the carrier frequency or this ACS?
This is the channel, carrier frequency. Yeah.
Okay.
See, so these are the ones that use it for millimeter wave, right? And yeah, this could be like less than 1 gigahertz. So this could be up to 3 gig, and this is up to, let's say, 6 gig. The radio frequency, basically, the FC, if you recall, the carrier frequency. And the latency is the latency that your applications can get, the traffic latency experienced by your user applications. Traffic delay, you can say. So if you want extremely low traffic delay, you will be going for higher numerologies. But they also have smaller cell size. Is that clear? And interestingly, you can see in the figure on the left hand side, even when you have the channel bandwidth, not the channel bandwidth, the carrier frequency less than 1 gig also, we can start using either numerology 0 or the numerology 1 or the numerology 2. And you can use numerology 0, 1 or 2 to relay small cell. And if you want to have medium size cell, then you'll be using the numerology 0 or 1. And if you want to have large cell, you have to use only numerology 0. Do you know why we have not written the numerology 1 and 2? Why we have not written these two here? When it is large cell, why we should not be using numerology 1 and 2? When the cell size is larger, I was just explaining what happens as the cell size grows.
Yes, sir. Yes.
What happens as the cell size increases, the propagation delay between the base station and the cell edge users increases. And you have to account for timing advance. So that means we need to have really larger,
The CP needs to be large.
but it is not possible to have larger CP if it is 30 and 60 kilohertz, right? So for this, it is not possible. In the case of 15 kilohertz, we have larger CP. That's the reason why you see, even though we can have 3 different numerologies available, when you take less than 1 gigahertz spectrum band, the operator have to choose between one of the numerologies depending on whether they are creating small cells, macro cells, or like medium size cells.
Yes, sir. Yeah.
Okay, I'm done from my side, and these are the references that you have. And apart from the textbooks, and I was also giving you the links related to this share tech note that some of you are mentioning yesterday. And there's one article from IEEE Explore on this NR bandwidth configurations and operations. You can go through it. And the last 2 things are related to calculating the transfer block size and the throughput as a function of numerology and number of MIMO layers, the coding rate and other things. So you can try playing with them to appreciate how things vary.